Right, good morning. So, what we're going to talk about? We're going to talk about software? Yeah, we're going to talk about software. In fact, what we're going to do first is we're going to take a selfie. Okay, is everybody good? You good? Got your best selfie face on? Let's just see how this one works out. Yeah, come on, smile. I can see some of you are not smiling. Come on. Yeah? Okay. Now, one of the things you will notice in this talk is there's a lot of photographs, because I take a lot of photographs. Part of that is to make the slides more interesting, so that when you're looking at the slides and you fall asleep, because, you know, it's Friday, you have something to look at. But something else here as well. We can do this because of software, because of the advances in software over the last couple of decades. Because software is absolutely everywhere. We tend to think of software as having this huge kind of effect. But as the introduction suggests, what I want to talk about today is the details. We tend to overlook the details, or rather, when we get caught up in the big narrative, what software can do for us in the big picture, we lose sight of the little picture. So I used to just put some simple details, but you may have noticed in the last year or two there's been some severe fragmentation in the social media space. So you can find me pretty much everywhere, okay, just to let you know. My parents were generous enough to give me an internet unique name before the internet was invented. That was a good move. I suggest you do this for your children if you have not already named your children. I did actually do this. I Googled both my kids' names, first and last name, and made sure they were internet unique. That's attention to detail, okay? I still remember my older son going on Twitter when he was 13, and then we said, okay, yeah, go on Twitter. And he said, what should I call myself? And, you know, all his friends are like, you know, John1234 or, you know, Crazy Cat 5. And I said, just use your first name and your last name. And he said, Dad, it's available. And I said, that moment was 13 years in the making, okay? So there's an idea here. Now, when it comes to introducing myself, there's a few things sometimes people know about me. Sometimes people know I have an interest in architecture. I have an interest in patterns. These two books I co-authored a number of years ago. Somebody once asked me, Kevlin, if I'm interested in design patterns and software architecture, should I read these books? My answer to you is no. You should read these books after the other 5 books that you've read. If you're still not bored, then read these. These are kind of very detailed. And they focus on very specific aspects. Personally, I am interested in the detail of code. I edited this book a few years back, an open source and crowdsourced book, 97 Things Every Programmer Should Know. During the first wave of lockdowns, Trisha G. and I finished 97 Things Every Java Programmer Should Know. But a lot of people, when they come to know me, actually associate me with something else. They associate me with failure screens. I said I take a lot of photographs. This is a photograph nearly 15 years ago, actually, Copenhagen Airport. You can see one of the most interesting things is that software development is responsible for the most accidental installation art on the planet. Okay? You are an artist. Okay? You didn't mean to be, but you are. And that's the point. We end up with this kind of like gorgeous matrix-like effect in the background. This happens a lot. And it's a good reminder to keep ourselves humble. It's just like, yeah, we run the world, but actually it kind of breaks every now and then. It's got to the point, because I keep taking these photographs, people start sending them to me. It's made the register, so it's become known as a Kevlin Heney. It's a humiliating public software failure, photographed and tweeted to the Eponymous account. I now get it on all social media. Kevlin Heney's are frequently seen at ATMs, supermarket checkouts, but the best ones usually occur at transport hubs where they enjoy the benefit of full displays. This is the first time somebody actually called it a Kevlin Heney screen in 2016. Arriving in Bologna, I saw a Kevlin Heney screen. I have been asked, Kevlin, what's it like to have your name associated with failure? Yeah, it's mixed. It got to the point, in 2016, I was doing a conference in Bristol, where I live, and the organizer of the conference, it was Agile in the City, the organizer of the conference, John Clapham, came up to me, and he said, I've just spotted a Kevlin Heney. And it's just like, I'm right here. downstairs. And he said, I want to take a photograph of you and then tag you in it so that you can retweet a Kevlin Heney with Kevlin Heney in it. So then we did it the next year as well. And then when I was showing this at DevTernity in Riga in 2017, we've kind of got this Inception-like effect. And it's even made it as far as Urban Dictionary. In fact, my wife started a new job recently, and they said, oh, so tell us about your husband. And it's like, he's an Urban Dictionary. It's like, yeah. I use Urban Dictionary to find out what my children are saying. But apparently that's relevant. And people ask me these questions, does this count as a Kevlin Heney? Yes, is the answer. But this also is important because when we come to think about software, we need to understand that software is an illusion. What we do is we create an illusion. We create the illusion that that is an ATM, but actually it's a universal computer. It allows you to potentially to do anything. We give people, our tool is a general purpose computation device. Potentially it can do anything. So this is the first way we need to think about it, because sometimes people get a little bit lost in complexity when they develop software. They say, oh, I'm generalizing something. Be really careful with that. You're already working on the most general thing you can possibly have. Yeah? I want this software to do something general. Okay, look, here's a compiler. That is the most general piece of software. Give it to your clients. If they want general software, give them a compiler and an operating system. They can build anything. People don't want general. What they want is specific. Yeah? Your job is to turn a general purpose anything into something specific. And that's an ATM. That is a particular client that will run to fulfill a particular goal. Whether that goal is in something medical, whether that goal is for personal banking. The point there is it's to do something specific. People don't want general. In order to do this, we need to have to pile on the details. Now, that's where it all gets interesting. If all of this is an illusion, when software fails, that's when the illusion breaks. It crashes to the floor, and your beautiful, specific application is now just a pile of error messages and tracebacks and log messages for everybody to see. Now, this beautiful phrase, Meyer Manny Lehman, in his paper back in 1980, made this observation. Any program is a model of a model within a theory of a model of an abstraction of some portion of the world or of some universe of discourse. I love this sentence, and I think he did too, because I can't imagine that he sat there and wrote this without thinking about it. I think he had a lot of fun with this. I also commend this to you as not only is it an accurate way of describing the hoops of abstraction and different layering that we go through, but next time one of the members of your family asks you, so what is it exactly that you do? Answer with this, because otherwise they will ask you to fix their computer. If you use this, they will never talk to you again about computers, okay? But there is a deep truth here. But there's a point here about a particular word, abstraction. We use it a lot in software. We use it a lot in technology in general. But we often forget what it means. If you're looking at code, we have terminology like abstract classes. When we talk about the grander architectures, we talk about layers of abstraction. When we talk about what skills we want from developers, we talk about the idea of, if they have good abstraction skills. But what does that mean? Abstraction is removal. Quite literally, that's what it means. It comes from the original, it comes from Latin. Abstrahere means to draw off, to remove, literally to draw off water, to abstract water. And we've generalized its meaning. We remove something. Abstract art is involves the removal of reality. An abstract class involves the removal of implementation. Abstraction is about removing stuff. Why do we do this? Edsger Dijkstra made the very important observation, because sometimes we get a little lost in our abstractions. The purpose of abstracting is not to be vague, but to create a new semantic level in which one can be absolutely precise. The skill of abstraction is not in removing things, but knowing what to remove. You want to get rid of stuff so that certain details shine through. Poor abstraction is where you end up waving your hands and nobody knows what you're talking about, and it's all vague, there's no commitment. So he uses the term semantic, and there's a bunch of phrases. that we sometimes use. You sometimes find them, we use them in arguments. Sometimes people say, oh, you know, that's just semantics. I've certainly had debates on philosophy, politics, computer science, AI, whatever, where somebody said, oh, yeah, but that's just semantics. And it's just like, but what does that mean? That's what it means. That's just meaning. You can't dismiss something by saying, oh, but that's just meaning, because that's the whole point of your argument. Particularly when we deal with software. What is a software system? A software system is an organizational structure of meaning. That's what it is. It's a system of meaning that a group of people have collaborated on. It's a system of meaning evolved in time. So to say it's just meaning kind of tells you exactly why it's not just meaning. We use the same kind of wording when we talk about details. It's just details, as if to dismiss them. But it turns out that one person's detail is actually another person's job, another person's design domain. It turns out that details matter. As the logician Alfred North Whitehead observed, we think in generalities, but we live in detail. That's where things actually happen. So the skill that we're after was captured in this wonderful quote by Will Gompertz in a book called Think Like an Artist. I said we were all artists, so let's figure this one out. We're talking about a very specific mindset that is crucial when it comes to the act of creating. And let's be very clear, jokes aside about failing software systems, software development is one of the most creative acts on the planet. And I sometimes get a little bit annoyed when developers will say, oh, you know, yeah, the creatives, and they're referring to people in a different department, often marketing or the UI designers and so on, the creatives, as if what you do in software, honestly, in software you are building something out of nothing. There is nothing more creative on the planet. Quite literally, I mean, in past centuries you would have been burnt at the stake as a witch, okay? You are literally casting spells upon stone, silicon, okay? You are casting magic, as far as most people are concerned. And they want you to fix it, by the way. So this is the point. When it comes to this act of creating something from nothing, it's an attitude that can be encapsulated in a simple but demanding rule. Always think both big picture and fine detail. It is easy to get trapped in one or the other. As a developer, you can get trapped in the detail of the moment. You're locked into your IDE. But sometimes if you're sitting in a meeting with your architect's hat on, you're kind of like all big swishy hand waves, and it all looks good because PowerPoint architecture never crashes. Okay? And whatever I draw on the whiteboard will always work because the whiteboard and my mind are a perfect virtual machine. But the minute it hits reality, that's where the detail matters. We use the metaphor of architecture extensively. So I will borrow from a site, Leewardists on architecture. What I love is the way they looked at this. Here's our view of architecture. It's the same in software. Here's what actually happens. People, life. It turns out that that beautiful PowerPoint architecture or marketecture that you had needs to actually meet the complexity of reality. And reality is a weird and complex place. So what is it that we're going to talk about when we talk about software? Sometimes people think of architecture as the big things. So they draw big boxes. The problem is that software is not about diagrams. A diagram is a convenient visualization. A sketch on a whiteboard is a convenient visualization. The words you use, they're convenient, but they're not the thing that is built. So what is big in software? And that's the problem, is it doesn't come with a natural scale of bigness. Although we use the architecture metaphor, bigness is not defined by physical scale. In the real world, big is defined in architecture with respect to the human scale. Okay? If you stand at the bottom of a tall building and you look up, it's big. Why? Because it's big with respect to the human scale. But what does that mean for software? How big is that? It turns out software doesn't have a size that is natural. I remember it was around, I don't know, it was just before 2000, there was a copy of Scientific American. Yeah, it would have been late 90s. There was a copy of Scientific American that talked about the mega engineering projects. Mega engineering projects. And it picked a few. It picked the Three Gorges Dam in China. Absolutely huge. If you've ever stood at the bottom of a large dam, it's massively impressive. And it's just like you look up and you go, this is big. This is a mega engineering project. They focused on the bridge across the Öresund connecting Denmark and Sweden. If you've ever been across that bridge or seen that, it's big. It looks impressive. And they had a number of other projects. They also focused on Windows 2000. And people kind of was like, what? Because that's big. It's actually more complex than a bridge. It is more complex than a dam. Software is some of the most complex stuff, but it's almost invisible. It doesn't look like anything. So Grady Booch's perspective on this is a really useful one. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change, not by physical scale. When we talk about software architecture, the bigness is to do with how much effort is involved in changing it. That's what makes it big. If somebody says, I can do that tomorrow morning, it's not architectural. If somebody does this, if they take in the breath, you know it's going to be architectural. If they say, yeah, we don't do that here, that's going to take us 6 months and would actually require a new budget and 5 extra teams, that's architectural. That's how you know something's architectural, not because you're standing at the bottom of it, but because somebody is not going to give you the time or the money. And this also affects some really interesting details, because sometimes we dismiss something as a detail. One of the hardest things in software development is naming things. And I'm going to say that's not just to do with naming in the code. For those of you not involved in code, this is all the way up. It's naming of the product. I mean, there's some really stupid product names out there, like X. That's just really stupid. Okay? Naming is hard. But how easy is it to change a name? Okay, let's look at this one. Clonable. For those of you who worked in Java, you may be familiar with this. It's an interface. It's been there since before the first release of Java. This is fundamental. It's in the core language. For those of you who might be doing .NET, I give you iClonable. Again, in there from the beginning. Part of the core language. Now, I'm going to present you with something else. Here's how you spell it in English. Oh, you mean there isn't another E there? No, there isn't. Now, a number of you are thinking, yeah, but English, it's got like this crazy spelling system. Some of you are thinking, yeah, but English doesn't have a system of spelling. And to those people, I say you are wrong. English has about 6 or 7 different systems of spelling, all at the same time. The problem is not that it doesn't have any, it's it has lots. Yeah, that's the difficulty. And in this particular case, they got it wrong. Now, did they know they got it? This is a detail. But here's the question. Is it architectural? Okay. How much effort would it cost Oracle and Microsoft to change? Well, from the point of view of the developer, absolutely nothing. I remove the E, and then I commit. And then the world falls apart. So the cost of the fix is not the cost of what the individual developer's doing, and this is the problem. If you get too lost in that focus, it's just a detail, it won't change. You forget that details are connected to everybody else. The world collapses. The world stops working. That is architecture. What you just did was equivalent to changing the laws of physics for a building. Okay, you've just pulled something out and changed a minor assumption. Did they know this? Yes, they did. Clonable is misspelled. This is a bug report. Dated 1996. It's dated before the first release of Java. They knew this was a problem. In fact, the bug report goes, clonable is spelled with only one E, clonable. Ask any geneticist, including my wife. Useful to have an authority on hand. Ask any English specialist, such as Henry McGilton. Now, what you may notice here is that English is not spelled correctly. I also had to look this one up. It turns out McGilton is not spelled correctly either. We actually have a term for this. It's called Muffrey's Law. Muffrey's Law, if you write anything correcting or criticizing the quality of somebody else's editing, proofing, spelling, grammar, etc., there will be some kind of editorial error in what you have written. You're feeling like, oh yeah, I'm going to correct this. The universe is going, I'm waiting for you. I've got you. So a respelling of Murphy's Law. Anything that can go wrong will go wrong. But that fun aside, this is embarrassing. Let's fix it before we ship. Why is this a big deal? Because right now, very little code relies on this typo. And this is an important concept. It doesn't, and although I'm picking on naming, it's just a detail. This applies to pretty much anything in an API. You choose a 32-bit integer to represent an idea. Turns out maybe 64-bit or a string was better. You choose something that takes 5 parameters, and suddenly you need 7. What is the flexibility of your API? As Josh Block, and we're going to come back to Josh in a bit, public APIs like diamonds are forever. The details count. The details are what actually ultimately create the work. And people, oh yeah, it's all about the big... No, that's what gets you in there. But the thing that causes work for future developers is normally in the details that we overlooked. By the way, there are some interesting consequences. This is the Wiktionary page for clonable. Spelt, as expected. But what I want to draw your attention to, alternative forms, especially in computing contexts, clonable with an E. It turns out that this spelling mistake back in 1995 into 1996 has now caused a respelling in the English language. It turns out if you do a small thing often enough, it becomes a big thing. That, again, is something that we are blind to. Again, when we think about software architecture, we think it's to do with the big things that are obvious. But guess what? If all of your developers are doing the same thing and it's little, lots of little things add up to be a big thing. This is why details matter. Keep your eye on these. So I'm going to come back to John Bentley as well. He published this book, Programming Pearls and then More Programming Pearls. And in this, he included a chapter on bumper sticker computer science, just simple quotes to keep in mind. There's a very simple one from Peter Weinberger, details count. I'll refer to the Mythical Man Month because ultimately everybody does. Mythical Man Month from the late Fred Brooks. This is a book that was written in the 1970s about a software project of the 1960s. We might question what relevance it has to us here in the 2020s. This is the second edition that was published in the 1990s, and it includes additional writings from Brooks of the 1980s. That's all very 20th century. Does it have relevance to us now? Well, yes, it does, not only as a work of history, but also as a reminder that no matter what else has changed in technology, human beings still behave like human beings. We haven't changed. We are surprisingly and embarrassingly consistent, as is the way that we run things. This classic project management advice from Brooks. How does a large software project get to be 1 year late? One day at a time. So, how do you get a large software project? How does a small software project get to be large? One detail at a time. All the details matter. They fit together or they don't, and that creates your extra work. And we are blind to this emergence. This emergence is also influenced by other aspects, us, the shape of the teams and the organizational culture, as to how we manage those details. This observation is also not new. This is taken from Melvin Conway's 1968 paper, How Do Committees Invent?, from which we get Conway's law, the idea that there is a forcing relationship between the structure of your architecture and the communication paths of your people. The way that people communicate influences the way that they develop. This is a very unsurprising result when you look at it like that. But he also makes a number of other observations. It's only a 4-page paper, so there's a load in there. But one of the observations he makes is the structures of large systems tend to disintegrate during development. You know, I love that terminology. I reread this recently, and I love the fact he used the word disintegrate. I don't think we use that often enough in software, particularly when we love the language of integration. I think we should also talk about the language of disintegration. It just falls apart. So disintegrate during development, qualitatively more so than with small systems. So a friend of mine, Rob Smallshirt, did this really interesting study back in 2014. Probably one of the most overlooked important papers, I would say, of the last decade. I, in fact, was not aware of it until the beginning of the pandemic. Predictive models of development teams and the systems they build. What he did is he created a simulation to understand the impact of teams and people and movement of people on software projects. You can see that this is a log-log scale. Lines of code and lines of code across the x-axis and the productivity, lines of code per year. Now, of course, we need to be cautious with using lines of code as a measure of anything other than lines of code, but it gives us a sense of size. I often ask people, tell me about how many lines of code you got in your system. I know some people don't like lines of code as a metric. I think they're wrong. Lines of code is the best metric you have for lines of code. There is no other substitute. If you want to know how much stuff people have to deal with. So in one organization, there was one team, 100,000 lines of code. One of their other teams was 1 million lines of code. That's just a difference in the amount of stuff. If you looked at the two teams, you could see the difference in their daily experience. The 100,000 liners tended to go home on time. The 1 million liners were always firefighting. What was interesting is that both systems had about the same amount of functionality. If you'd written it out in function points or user stories, you'd have ended up with roughly the same number. But one team was dealing with unnecessary details, while the other had necessary details. This team had tests. They had good documentation. They had good code reviews. This team, what are tests? So there is a difference. Productivity is a function of code base size. This is the most important one of the most important observations Rob makes. The more code you have, the more stuff you have, the slower you will go. Simple as that. And there are no exceptions to this rule that I have found. This starts to make us think about legacy organizations with their legacy systems. Developers are dramatically less productive on larger bodies of code, by an order of magnitude or more. He also looked at the life cycle of these projects. And interesting observation, if you have a 20-year project, then the current developers the people on the current team were only responsible for 20% of that code, statistically. Basically, that means 80% of the code is somebody else's. And we don't know why. We don't know why it's here. We don't touch it. We end up with the accumulation of unnecessary details that detract from what we're trying to do. We end up fighting the existing code base or being frightened of it. In fact, Rob has quite a nice model. He looks at a number of things. He looks at the half-life of various artifacts. So half-life, just to clarify, half-life as opposed to averages, so be very careful with this. Half-life is a term that we get typically from radioactivity. If I have a lump of plutonium in my hand, a kilogram of, well, actually, I'll be dead. But if I have a kilogram of plutonium in my hand, in 20,000 years, I will have 500 grams, because that's the half-life of plutonium. In another 20,000 years, I'll have 250 grams. In another 20,000 years, I will have 125 grams. I will also be far older than human civilization, so I don't think that's going to happen. But there's a number of interesting observations here. One is that developers on a team, half-life of about 3 years. Windows XP, I still see installations of Windows XP roughly halves every 5 years. He wrote this in 2014. Based on my experience with failure screens, it's still true. It's still decaying. There will still be, my children's children will still have Windows XP failure screens in their life. Just very few. Applications, 6 years. CEOs actually last quite a long time compared to developers. Half-life of 7 years. But now it gets interesting. Now it gets interesting. That line of code you wrote yesterday, there's a 50-50 chance that in 2036, that line of code will still exist. Oh, it's just details. Yeah, what do you think software is? It's just the details. Let's see, classes. You're working in Java, you're working in Python, you're working in JavaScript. You wrote a class this week, there's a really good chance that in 2060, it will still be alive. 50-50. a module or subsystem or something more significant, I mean, I'm going to be dead by the time that that goes. This is really interesting because the point is the stuff you just throw out without thinking about it, we tend not to come back to. Rob also looked at the observation goes beyond Conway's law. He said, if we're developing, imagine 7 developers on a 5-year development, starting from a greenfield situation. Here's their contribution to the code base. You will notice that all of these there's lines and then the color goes dim. What does that mean? It means the developer left the team. This is the interesting thing that we underestimate. It's obvious when you point it out, but when you visualize it, it's even more compelling. The idea is that your effect will live on long after you have. I've left the team. Yeah, you're still contributing on a daily basis. 5 years later. There are systems that I've worked on in the electricity industry in the 1990s that I think are still quite happily running out there, and my code decisions, based on whatever day of the week it was and how I felt when I was at work, are living into the 21st century. The point that Rob makes is not simply that there is a structural relationship between your organization and your architecture, but with time, the structure of your software reflects the organizational structure integrated over time. Now, when we start talking about these issues, we often frame it in terms of technical debt. People like this metaphor, but the problem is I've noticed with many people in software, they start using technical debt to mean bad code. That's not what the debt metaphor is about. Of course, some debt is bad, but some debt is intentionally good and deliberate. Debt is not just another word for bad. The problem that most teams are experiencing is not the problem of debt. If you like, that's an effect. Don't confuse cause and effect. Yeah, a lot of people say, oh, we have a technical debt problem. No, you don't. You have a technical neglect problem. The problem is not that you have the debt, the problem is how you got it. And most teams end up with a situation they're not paying attention to the detail. That's how you create legacy systems. It's not so much the issue of that we have debt. The question you have to ask is not do we fix the debt, but how do we avoid having it in the first place? Now, there are a number of examples. Let me focus on testing for a moment. So this is a 2016 report, IEEE conference. Wolfgang Trümmler and Francis Paulisch did this. They're Siemens Healthcare. I was actually involved in some of the training and workshops that contributed to this, so this was a nice result. How specification by example, also known as behavior-driven development, and test-driven development help to avoid technical debt. So it's an industrial experience report, and one of the things that is interesting, the resulting data show a very low defect density can be achieved with these practices. Basically, testing in a way that is not just about testing, but about communication, which helps to avoid technical debt introduced, for example, by quick fixes during a late product phase. There's an idea there about, as it were, countering the force of neglect. Neglect is a thing that you don't do. Yeah? By the way, that's why, by the way, it's very difficult for people to see neglect. Neglect is a thing that doesn't happen. It's not a thing that happens. Oh, just like that was perfect. A thing that doesn't happen, like sound. Hopefully somebody's going to run on stage at this point. Ah, no. There we go. It's a fig. No. Yeah, technology runs the world. Somebody backstage? I was just going to shout and hope that it doesn't break the mic. Okay, let's just go with that. Do we know that testing is useful? Yeah, this is a paper from 2014. Simple testing can prevent most critical failures. I love titles like this because they tell you, if somebody says, so Kevlin, what's this paper about? What does this paper tell us? Well, it tells us that simple testing can prevent most critical failures. There's no mystery in the title. More importantly is the subtitle. An analysis of production failures in distributed data-intensive systems. In other words, this is not just like, we've not just run an experiment on a bunch of first-year computer science students. We've actually gone out into the industry and looked at distributed middleware, and because all of the bug lists are public for these open source projects, we can actually see what happens. We can recreate the situations. And we often think, again, oh, big systems, therefore big failures are responsible for things. Oh, Kevlin, unit testing is not going to help us because we're talking about big systems. I often have people trying to convince me that the bigness of their system is really important. That's great until you look at the numbers. The majority of the production failures, 77%, can be reproduced by a unit test. I don't care how big your system is, the chances are, if you're experiencing big failures, there's a 3/4 chance that we could have found that with a unit test. And more importantly, our blind spots. Almost all catastrophic failures are the result of incorrect handling of non-fatal errors. Yeah, in other words, oh, we've got an error and we'll do something, but we never test that path. So when it gets executed, bad things happen. So this is all good. And this would be great because obviously every developer in every organization working on every code base writes lots of tests. What does the evidence tell us? Well, this was a study completed in 2019. And it was effectively a longitudinal study of about 2,500 developers over 2.5 years. So again, it's not a simple test on a Friday morning, bring a bunch of developers in and see how they code. This is actually instrumenting their IDEs. And the most important thing here is the languages they chose. Oops, we've cut out again. Test, test, test. We here? We here? We here? No, we're not here. I'm just going to shout very, very loudly. You can all hear me? I would say raise your hand if you can't hear me, but that's not going to work very well, is it? Ah, there we go. What is interesting is they chose C# and Java. Why is that interesting? Because C# and Java are two programming languages we consider relatively modern, but most importantly, these are two languages that are very much defined by their IDE culture. You tend not to find C# developers and Java developers who don't use an IDE, who just use a regular editor. In other words, they are locked into an environment, and so therefore, instrumenting the environment is meaningful. You don't tend to find Java and .NET developers using Vim or Emacs or anything like that, or Sublime, so on. So what do we find? It turns out the most popular development strategy or testing strategy is to not test. Sometimes I ask people this in workshops, so tell me what you think the most popular testing approach is. Some people go, oh, TDD, and I say, no, it's not going to be TDD. Just good old-fashioned unit testing, no integration testing, no. And then somebody says, no testing. Well done, that is the most popular approach to testing, is to not test. What we find is that in these languages, and importantly, these languages are languages where the test culture is actually quite strong. That there is a well-defined concept of the test culture that has revolved around JUnit and NUnit and so on. Half the developers in our study do not test. Developers rarely run their tests in the IDE. Because it's an IDE-centric culture, no, they're not sneaking outside the IDE to run their tests. We know that if they're not running in their IDE, they're not running them. Most programming sessions end without any test execution. Now, does this matter? Well, this isn't really a talk in the 2020s unless I talk about AI, at least for 30 seconds. There'll be other talks on AI, but what I want to do is I want to offer you an observation here. Testing is very much about the details. What we may have ended up doing, if we're not careful, some developers will be very good with this, but our evidence suggests that most won't be. An observation I made a while back, well, not that far back, April. The practical consequences of using large language models to generate code is many developers will find they have unwittingly moved themselves into a role they were probably trying to avoid. They have automated the creation of legacy code. Oh, I can be so much more productive by using ChatGPT or Copilot or, yeah, this is brilliant. What you're actually doing is creating legacy code because you didn't write it. Yeah, this is the standard definition most developers use for legacy code. What is legacy code? Again, I run workshops on this. I ask people, what is legacy code? They come up with lots of definitions, but always at least one person says code written by somebody else. That's legacy code. If my colleague writes code, it's legacy code. If I write code, it's awesome. That's the standard definition. Guess what? If you are using AI, you have just created legacy code. Congratulations. In English, we call that an own goal. You've just scored against yourself. Now, you don't have to have scored against yourself, but the way that most people, and redefine their job as debugging and fixing such code. My experience so far is that most developers do not check the code. What they do is they check it in, which is completely different. And then they have a problem with it. And because they often don't test it, they often don't review it, they miss this. It's just details. Yeah, it turns out it's kind of important. So our challenge here, I said we'd come back to John Bentley. Our challenge here is, how do we write correct programs? Now, John Bentley 40 years ago, wrote this article in Communications of the ACM, writing correct programs. So is this the answer? Well, what he did is he took a simple algorithm, not any of the big systems we're talking about, simple algorithm, to do a binary search. And actually, this algorithm was actually quite novel at the time. And it's been used extensively since. You can actually find it implemented in a number of libraries. It uses a three-way comparison. And the thing that Bentley did is that he proved, in other words, here's the statement with assertions and assumptions, he proved that this works. In fact, one of his students was Josh Block, who I mentioned earlier on. Josh went and implemented exactly that. You can actually see the three-way partitioning. Oops, let's go back to where we can see it. The three-way is actually visible in Josh's code. Down here is this if, else, if, else. This was part of the Java library. This implementation was part of the Java library until 2006. It has a problem. It turns out it has a bug. It turns out that when you add two numbers together and divide them by 2, that it does not behave like two numbers being added together and dividing them by 2. Because it turns out that of all the assumptions that we have when we are creating a model within an abstraction of a model of some, etc., we may have left out something, a small detail. We may have left out the fact that integers are not integers. That sounds like one of those crazy kind of koans. Then it doesn't work. When you add a really big number to another really big number, it does not make a bigger number, it makes a negative number. Oops. This was not discovered until people started creating really large arrays because they had many gigabytes of memory. You couldn't have this problem until the physical aspects of computing allowed them to happen. The assumption is actually visible in the original one. He assumes perfect arithmetic. In fact, Edgar Dijkstra, a number of years before, in fact, over a decade before, actually highlighted in structured programming, he said, I have assumed perfect arithmetic. He was talking about a proof that he'd just done. I have assumed perfect arithmetic, and in my experience, the validity of such proofs often gets questioned by people who argue that in practice, one never has perfect arithmetic at one's disposal. Admissible integer values usually have an absolute upper bound. Real numbers are only represented to a finite accuracy, etc. So what is the validity of such proofs? So again, there was a kind of whole phase a few years ago where people go, oh, we can prove this to be correct. You can only prove with respect to your assumptions, and your assumptions you're often blind to. As he says, if one proves the correctness of a program, assuming an idealized perfect world, one should not be amazed if something goes wrong when this ideal program gets executed by an imperfect implementation. So 3 weeks ago, in Japan, Toyota automatically shut down some of its factories. Guess what? They'd overlooked the fact that disk space is finite. And there was a piece of code that assumed that every write will be successful. Guess what? You are not guaranteed that. The universe does not guarantee that. There's a bunch of things the universe does not guarantee. Oh, it's just a detail. Yeah, it's a little piece of error handling that wasn't there. And instead, the whole factory shut down. Beautiful quote from Aldous Huxley, reality cannot be ignored except at a price. We often work. Developers, I often see a lot of code is written with the assumption we have infinite memory. The network always works. We have infinite disk space. Every value that is given to me is always going to be correct. Yeah, it turns out that's where the fun happens. So going back to this, the simplest way of fixing it is to use something different. Mathematically, these are equivalent. But in practice, they are not equivalent. That's a kind of an important distinction that we have there. So what we learn from this, Josh Block highlights, the general lesson I take away from this bug is humility. It is hard to write even the smallest piece of code correctly, because there are details that will interfere with it, details that can dominate that you are not aware of. Paying attention to the little details actually matters, because that's how software is built. It doesn't matter what the big structure is, the smallest detail can bring it to the ground. Our whole world runs on big, complex pieces of code. When we start thinking about dependencies, so sometimes when I kind of quote figures, and I start saying, oh, you know, this many this many lines of code, there's always somebody in the crowd. You might be that person. There's always at least one person who says, oh, that's okay, we're developing microservices. That solves the problem of big code bases. No, you still have a lot of code. And now it has more complex failure modes. Yeah? Microservices can be used, A, to simplify something, B, to make no difference at all, C, to make things complex and slow and difficult and buggy. Most companies seem to opt for version C. Choosing an architectural style does not cause magic, because there is no such thing as magic. Even if you're burnt at the stake for it, there is no such thing as magic. To get to option A, you need to pay attention to the details. That's what makes the difference between a team that is able to do that and a team that is not. We find sometimes, even when we focus on correctness, and we think we're doing the right thing with details, we can often be surprised. So why have I put this up, The Making of a Fly? What has that got to do with anything? It's a book by Peter Lawrence, The Genetics of Animal Design. What's that got to do with software development? Well, initially, not a lot, but it's a very cautionary tale from just over 10 years ago. It turns out that The Making of a Fly was available on Amazon. But not Amazon selling it, but booksellers on Amazon selling it. And there are a couple of things I want you to notice here. You can buy it for 1.7 million US dollars. That must be one hell of a book. There's another book vendor that's selling it for just over $2 million. Well, that's kind of where am I going to get the extra $500,000 from? You know, but by the way, if you buy it used, you can buy it for $35. Wait a minute. So I can buy it first-hand, new, for about $2 million, or I can buy it second-hand for $35. That's a really difficult choice. How did this happen? So Michael Eisen noticed this, and he observed something. He observed the behavior of these two pricing sources, these two book agents, over a successive period of days. And what he observed is that there was a constant ratio. That one of them had a ratio with respect to the other of 0.99. So that's the vendor Profnath. 0.9. So basically what they're doing is they are offering, this is the standard thing you get in marketplaces, we will offer the lowest price. So there is a piece of software here that is automated that automatically checks the market, finds the lowest price, and then offers something just a fraction of a percent under that. So if you're offering something for $100, we'll offer it for $99.83, and we can claim that we have the lowest price. And that algorithm runs every day. However, there's only one other vendor in the market. They have a different strategy. They put in a 27% markup. What's going on? Well, it turns out that Profnath has the book. The other ones, Bordy Books, do not have the book. Their proposition is, you pay us, we'll go and buy it, and then we'll sell it on at 27% profit for us. And their strategy is, we'll take whatever price is the highest price, the lowest price in the market that's current, other than us, and mark it up by 27%. This reached nearly $24 million before somebody pulled the plug. What I want to highlight here is that individually, each of these strategies, each of these pieces of code was correct according to its limited assumptions, individually. But when combined, they created a new system that ran out of control. We actually see this in terms of flash crashes. This is from 2016. As you may have noticed, I'm from the UK. We've been running a social experiment for the last 8 years, that's not been very successful, and has kind of helped trash the economy. But even Brexit cannot cause a crash like that. because humans are not fast enough. I want you to notice that on this axis, that this market crash happened over a period. It dropped a significant amount of its value. The pound dropped nearly 10% of its value over a period of minutes. Honestly, humans are, we can be quite stupid, but we're not fast enough to be this stupid. Yeah? If you want to be this stupid this fast, you need computers. An observation from Earl Wiener, who's known for his work in safety, aircraft safety. Digital devices tune out small errors while creating opportunities for large errors. We actually had an experience of this recently in the UK at the end of August. Huge air traffic control failure that caused 3 days of traffic chaos. Thousands of flights were cancelled, hundreds of thousands of people were stranded. All because the National Air Traffic Service software shut down. I mean, they didn't actually close the airspace, but it meant that all the air traffic controllers had to do this manually. Turns out that doing this manually is a lot slower than doing it. Doing the right thing with computers is also fast, but it turns out the cause of the problem. What was the technical failure? The automatic flight planning system used by NATS, the company that provides National Air Traffic Control Services, was out of action for several hours. It was only out of action for a few hours, but it caused this ripple effect of many days. What was the cause? Triggered by a single piece of data in a flight plan that was wrongly input to its system by an unnamed airline. In other words, it was incorrect data. But it was, if you actually read the report, which I've done recently, Major Incident Preliminary Report, they point out the assumption. There is an assumption here about the uniqueness of waypoint codes in an air traffic control system. This assumption is not valid, and they've got lots of workaround code. In fact, they describe the algorithm. If you are looking at this from the point of view of a developer, it's fairly easy to see what's wrong with it. If somebody wrote it out, you could say, oh, you should test that. Here's a case that might fail. But they didn't. And that has led to this problem. As I've described here, it reveals an assumption. It's an assumption about a detail. Epistemologically speaking, in other words, the way we understand knowledge, assumptions are like Lego bricks in the dark. Okay? If you've never stepped on a Lego brick barefoot in the dark, I invite you to do that at least once. It's an interesting experience. An assumption is a curious piece of knowledge because you don't know that you have it until you know that it's wrong. You say, your colleague may say, oh, yeah, we're going to do this, but this is how we're going to deploy. Or actually, that framework doesn't work the way you thought it did. And you go, oh, I had assumed that. Up until that moment, you didn't know you had that assumption. The moment it's been shown to be wrong, you suddenly discover you had an assumption. It's a very curious piece of knowledge. It's like being told, by the way, here is a dark room, you have no light, you have bare feet, there are Lego bricks on the floor. I've told you there are Lego bricks, I've told you you have assumptions, but you won't know where they are until you've stepped on, oh, the system's gone down. It's disintegrated. So, I want to question the narrative that we use, because I want us to focus on details. We have this narrative running around the industry, move fast and break things. No, I don't think so. Move slow and mend things. Details matter. Move slow and pay attention. Okay? That is the skill. The skill is a more subtle one than we keep talking about. So, I'll kind of bring this talk to a close. If you have any questions, please ask them on the app. We'll try and give some time to answering that, but we're running a few minutes late, but hopefully we can get through some questions. This book from the artist, Austin Kleon, he's written some really good stuff, but again, for anybody who's creative, which is all of us, he observes it's impossible to pay proper attention to your life if you are hurtling along at lightning speed. When your job is to see things that other people don't, and that is your job. When we are focused on software development, no matter what our role, our job is to see the things that other people can't see. It's not just to see the big hand-wavy stuff. It's to understand that software is made of details, that we have to pay attention. Because the details are what provide us, or don't provide us, with work. They provide us with surprise. They provide us with capability. They provide us with delay, depending on how we approach them. Our job is to see the details. It's a skill of slowing down. So I'll close with the contemplation from a kind of classic book, Zen and the Art of Motorcycle Maintenance. Honestly, I don't know much about motorcycles except what I learned in this book. I've read this book a couple of times, and there's this wonderful observation. Normally, screws are so cheap and small and simple, you think of them as unimportant. But right now, as your quality awareness becomes stronger, you realize this one individual particular screw. And he's talking about a screw that is jammed into the engine of a motorcycle. This one individual particular screw is neither cheap nor small nor unimportant. Right now, the screw is worth exactly the selling price of the whole motorcycle. Because the motorcycle is actually valueless until you get the screw out. That's the point. That's the point. With this reevaluation of the screw comes a willingness to expand your knowledge of it. And I would say this is not just true of motorcycles. It is certainly more true of software. Thank you very much. I don't know if we've got time for...
Thank you. Thank you very much, Kevlin.
Thank you very much.
This was quite inspiring. So we do have some questions here, and just a brief reminder for everybody, questions for our speakers can be made through the application. So if you have any questions for any of the speakers today, just put them in the app.
Also, you can actually talk, by the way, we are in the real world. Hello.
Yeah.
This is not a Zoom screen. You can also speak to me directly. Okay, just to remind you, yeah? It's not like, oh, I'm just going to leave meeting. No, you're here.
If you like a more personal approach, there is a mic over there, so you can ask for it. Until then, I do have a couple of questions here.
Great.
So what about misleading details? Can they distract us too?
Yep.
And how to recognize them?
Okay, so one of my closing recommendations was we need to pay attention, because the point is the details matter. It's not just that they're important because they're good, it's that sometimes they are important because they're misleading. But you don't know that until you look at them. So can I give you a perfect strategy for finding details? No. Can I give you a general strategy for unearthing details? It's a statistical thing. It's a probabilistic thing. What I want to do is say, well, the more we look at them, the more we see. The more you walk into that room with the Lego bricks, the more Lego bricks you will step on. Okay, that sounds very painful, but by the way, in case you didn't know, there are actually shoes designed for Lego bricks, it turns out. The point is, if you're constantly running tests, if you're constantly running code reviews, if you're constantly looking at old code that has not been looked at for a long time, I'm one of those people that doesn't have this belief that many people have, oh, it's old code, it works, let's leave it. It's old code, we should look at it. Because it's old code, we don't know why it's there. If it's a 20-year project, then the chances are that we don't know who wrote it and why it's there. Check it. Review it. Just because it's old doesn't mean it's right. So I can't tell you how to find the misleading details. I can just tell you that the more you look, the more you will see. But if you don't look for them, they will come and bite you. They will discover you if you don't discover them. So I want to kind of change your attitude to one of engagement. Go looking for them. I can't promise you'll find everything, but if you don't go looking for them, they will come looking for you.
Thank you, and there are a lot of questions here, but we have not that much time. But there is one more question here. How to balance between analyzing details for too long and getting something done?
Oh, that's a really good question. Yeah, sometimes we can end up with an analysis paralysis. The trick out of that is to first of all recognize that you're in it. One of the best ways to recognize that you're in it is either exceptional self-awareness, ADHD medication, or your colleagues. Don't do this alone. This is one of the most important things is to do with group intelligence. Collectively, software development is a team sport. Okay? We have the potential to be smarter than individually. Rely on somebody else. Lean on somebody else. They will see things you can't see. They don't have perfect vision either. You will see things they can't see. But the idea is, the way to do that, to break out of that cycle, is to be talking, constantly communicating. The communication patterns that we have influence the software. And unfortunately, we have a culture, and I know this very, very much within myself, that, oh, I will just work on this until I've fixed it, and then I will present you with a solution. Let me just another day, just another week, just another year. But if you talk to somebody, it will reveal a different path. It breaks that cycle. And you go, oh, why don't we just try implementing this here? Oh, yeah, but I'm not sure I'm ready. Let's just try. That will break the cycle. It's like taking a cold shower, okay? It will break the cycle. So implementation, just trying something, remember, there is a softness to implementation. It's called software for a reason. When you commit, you can also roll back. You can experiment. You can throw it away. This is not like the physical world. I can try something, and it doesn't cost me anything to run an experiment. And I can throw it away. When you write a line of code, it's not necessarily a commitment. You can try something, and that's okay. That's a process of discovery, and that's part of the engagement. If I write that, it will raise new questions or make me suddenly realize, oh, I've overlooked a detail.
Thank you so much.
Thank you very much.
Can we have a applause for Kevlin?